Hi, so welcome to week 6 of the course Combinatorics 2 at Stockholm University. And so this week and the next one, we will talk about recurrence relations and how to solve them. And so today we will talk about homogeneous recurrence relations. So this is 10.1 and 2 in the book. And so what's the idea? The idea is if you have a sequence of numbers, and whenever you know the previous numbers, there's a rule how we can come up with the next number in that sequence, and that rule is called a recurrence relation. And so let's look at some examples here. For instance, here's a recurrence relation. an plus 1 should be equal to 2 times an. And so if you think about it, well, that's a nice rule, but the goal is always to come up with like an explicit formula for that sequence, if it's possible. And so let's say, so if you think about it, in this case, so we start from 0, so we're counting from 0. The indices start at 0, so it's a0, a1, a2, a3. And so, so if you know what a0 is, then this tells us that a1 is equal to 2 times a0, a2 is equal to 2 times a1, and so forth. So this is something which is not so hard to solve. Well, if we have a0, next one is 2a0, the next one is 2 times 2a0, which is 2 square a0, and then the next one is 2 times 2, 2a0, and so forth. So this will be the sequence. And that means in formulas that an is equal to 2 to the n times a0. And this is true for all the n greater or equal than 0. And this is now an explicit formula. Once you know what a0 is, so a0 is the initial value of your recurrence and of your sequence. And so if you know what a0 is, you know all the other values. And this is an example of such a homogeneous recurrence relation of order 1. Now, here's another example. And that example is like, in many cases, actually the hard steps. So there are kind of 2 steps. If you have a combinatorial problem and you want to count and want to solve it, and you're counting something and you want to know a rule maybe for these numbers. And so the first thing is you have to come up with a recurrence relation. Actually, that is often the hardest step, because as we will see, for the second step, once you have a recurrence relation, to find out a rule for the sequence, that's something which is quite technical, but there's a procedure in many cases how to do that. That's what we're going to learn about. But in the book, there are many, many great examples that show you where you can learn how to come up with a recurrence relation in the first place if you have a problem. So let's just do one here. So here, an should denote the number of all the expressions of length n where you use digits and operators. And so the digits should be 0 up to 9, and the operator should be plus, multiply, and subtract symbol. And the only constraint here is that no operators are next to each other. So for instance, so some examples here would be maybe 0 plus 3 minus 75. Okay, sorry. Okay, anyway, so the important thing here is that this is a valid expression, while if it would be like a minus and then a star, that's not allowed. Okay, and so we want to count them for every n, how many are there. And so how do you do that? Well, the idea is, well, you think about it, you have your expression, and you look at the very last digit or operator, and there are essentially like 2 cases here. So the first case is that this is a digit. Okay, this is a digit. And once we have a digit, are there any, what are the rules for these expressions? Well, these are just any expression of length n minus 1, where no operators are next to each other. So precisely once we're counting, and there are no more restrictions here. So here there could be an operator, there could be a digit, anything. So you can use a n minus 1 of these expressions you can just write here. And when you add a digit, you get another nice expression. So for instance, here we could just add another 9. But there's also a second case that in the last one there's an operator at the last position. Now here's I have to be a little more careful, because that means that there cannot be an operator here. So it means that here has to be a digit. But now once we're here there are no more constraints. It can be any expression of this form. So using this, we can now count an, the number of these expressions of length n, because we have now essentially two situations, so the rule of sum. And here we have digits. How many digits do we have? We have 10 digits. And for every of the digits, we can take any of the expressions of length n minus 1. And so this is now the rule of product. We have like 10 times an minus 1 plus so here we have 3 operators. Here we have 10 digits. And here we have n minus 2, because this is now length n minus 2. Many possibilities. So by the rule of product, we get 3 times 10 is 30 times n minus 2. And so this holds, well, whenever you can do this argument, you can actually make it reasonable for n greater than 2, but maybe you want to do n greater than 3. In any case, this is the recurrence relation, kind of a rule that tells you, so this should be the 2, how to find an once you know an minus 1 and an minus 2. So the next step is to learn how to solve these expressions. And in the book, they really focus on this case. So they focus on what could be called second order linear homogeneous recurrence relation. So recurrence relation is often abbreviated as R dot, namely the following one, an plus. Okay, so this is the expression an plus constant, so this is a constant, times an minus 1 plus constant times an minus 2, and so usually should start from 2. That means if you have it starts with a2 plus c1, a1 plus c2, a0, so the index starts from 0, so we start with a0, a1, a2, and so forth. And so this is precisely of the type we've seen above. Well, there was a minus here, if you think about it, but doesn't mind because it's, can put this all in the constant. So this is what we really would like to solve. And, well, we need the initial values. So a0 and a1, because this really is important where you start with. Because if you start with a different initial value, even if you have the same rule, of course, you will get something else. Maybe think about the 2 to the n times a0 example we've seen before. You get different solutions for different a0s. So here we have 2 initial values. You have to know what a0 is, so you have to know what a1 is. But once you know this, you can figure out what a2 is, because a2 plus c1, a1 plus c2, a0 is 0. So you can solve for a2. And then you know what a3 is, because you know what a2 and a1 is, and so forth. Now, what's the approach how to come up with a closed expression? That's what we want to have. The idea is to use what we've seen in our very first example as like a basic idea. So The idea is you plug in an, maybe that's actually better to say it like this, plug in something of the form a constant times r to the n. Think about the a0 times 2 to the n example. Okay, and a should generally be non-zero, r should be non-zero. But this is actually not so important. Important is now, if you plug this in, what do you get? Okay, let's plug this in here. So think of this as being an. So we get a times r to the n plus c1. Now, let's plug this in for n minus 1. So this is a times r to the n minus 1 plus c2 a times r n minus 2 should be equal to 0 for all the greater than 2. Okay, and well, what's happening here is, well, as I said, a should be non-zero, so you can just cancel this. And what else? Well, also r, think of it as being non-zero. In that case, we divide out the largest power, which is r to the n minus 2. So we get here an r, and we get here r squared. So this essentially tells you that this is 0 if r squared plus c1 r plus c2 is equal to 0. And this is an important equation, and you see it's very easy to get this equation from up here. So it's a quadratic equation, and this is called the characteristic equation. And its roots are called the characteristic roots. So R1, which is okay, and so let's say this is a plus case. This is a minus case. Well, in any case, so here we see that this is called also of order 2 because this is an equation of order 2. And if you see also here now, there are several possibilities which can occur. I mean, whenever we have a quadratic equation, if you think about it, so we have 3 cases. So the first one is that the solutions are both real, but different. When does this happen? Well, look at this expression under the square, the discriminant. If that is bigger than 0, it's a nice positive real number, and we get, and so these two will be different, but real. The second case is that this is negative. In that case, well, you're in trouble if you don't know complex numbers, because you'll get a complex number here. And then that's the case that it's actually equal to 0. In that case, these two are the same, so they are real but double roots. And so we will next consider these 3 cases. So let's look at the first case. That's case A in the book. R1, R2 are distinct real numbers. And so let's just do one working example, which is actually very kind of like an example you see most of the features which come up here. So namely this sequence, 0, 1, 1, 2, 3, 5, 8. I hope I didn't make a mistake here. So this is the, probably recognize it, the famous Fibonacci sequence, because what's the rule? The rule is that whenever you take, you always take just the sum of the 2 numbers and you get the next one. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, and so forth. So what's the recurrence relation? Well, the recurrence relation is that an minus an minus 1 minus an minus 2 is equal to 0 and greater or equal than 2. Okay, so check it out. So I already wrote it in the way we've seen it above. So if you bring it on the other side, it just means that an is equal to an minus 1 plus an minus 2. And so again, here we start from a0. And so the initial values here are A0 is 0, A1 is 1. Okay, and so what's the characteristic equation? We already seen how to do that. Well, it's just r squared minus r minus 1 equals 0. So it's let's solve this. So the characteristic, the two characteristic roots, r1 and r2, are just 1 plus minus square root of 5 divided by 2. So r1 is 1 plus square root of 5 divided by 2, and r2 is 1 minus square root of 5 divided by 2. So, and of course here in there you see the famous golden ratio. Okay, so how do we proceed from here? So what we've seen is the following. If you use a characteristic root and we look at A1 times the characteristic root R1 to the n, so some constant time this, when we've seen just before, because it solves this equation, equivalently this expression solves the recurrence relation. It's precisely what we see. Which means that this is a nice solution of a recurrence relation. It might not be the one we're looking for, but it is one. But in the same way, we get another possible solution. Namely this one here. Again, another solution. And now you can check, whenever you have two solutions of such an equation as before, you can add them and it will still satisfy the recurrence relation. This is why these systems are called, so these recurrence relations are called linear. If you know about linear algebra, this is where this comes from. And also, maybe at this point already can make a point that this is all very, very similar to linear differential equations. And so if you know about this, everything here will be very familiar to you. So we get even more solutions here by just adding them up. Now I claim that this is, we can actually, it is possible to show this is equal to a choice of A1 and choice of A2 will be actually equal to the one solution we want. Okay, so how do we see that? Well, the left side satisfies the recurrence relation and the right side too. So essentially all we have to show is that they agree on the initial values, because from then on everything else will be determined. So let's just check this. So we need that 0 is our A0, and so A0, and that should be equal to, well, this to the 0, just 1, this to the 0 again, so it's just A1 plus A2. And on the other hand, let's plug in A1, which is 1, should be equal to, now we plug in 1 here, so to A1 times R1 plus A2 times R2. Right? And so now what you see is, and this is how it will always work out in this case, we have two unknowns, A1 and A2, but we also have two linear equations. So we can solve them, and if you do that, I'll leave that up to you. We'll find out that A1 is 1 over square root of 5, and A2 will be minus 1 over square root of 5. So this means that, from this we get that if we choose these two parameters, then the right side will actually satisfy the same recurrence relation as the left side, and it will agree on the first initial value, so that will be the same. So we'll see that an is equal to 1 over square root of 5 times 1 plus square root of 5 over 2 to n. And now the same here, minus 1 over square root of 5. So here I already multiplied this out. So this is A1 times R1 to the n plus A2, which is minus 1 over square root of 5 times R2 to the n. And you can, of course, try to make this even look nicer. Now this holds for all n greater or equal than 0. So this solves this case. So let's talk about case B, complex number case. So in this case, R1 and R2 are distinct complex numbers. By this, of course, I mean complex, not real. Okay, so let's just make sure again write out what it is. So it was minus C1 plus square root C1. So this is our R1, and this was our R2. And so so this is now a negative number, strictly negative number. So this gives you you can now use the complex numbers to solve this. So we need I. And so if you do that, you get minus C1 divided by 2 plus, now we take the minus 1 out, square root of minus 1, which is I. And we get this, which is now a nice real number. So this is like a real number x plus I times a real number y. And what happens for the other case? Well, we just get the minus here. So in this case, I don't even, well, I can write it out. 2. This is x minus I times I. So this is the so-called complex conjugate. Okay, and now we can just do the very same thing. So I won't even do this with all the details. Namely, again, you can use this R1 now a complex number. You can still take powers to it, and it will still satisfy the recurrence relation. And you can do the same thing for R2 to the n, will still satisfy relation. You can add them, same thing, and now we will equate it with an, and we only have to solve, again, initial conditions, just as is seen above. And we can just do the very same thing as above in order to solve it for it. Okay, and so there's maybe one. So please look at the examples in the book. There's only one little thing I would like to say now. Namely, if you look at these examples, you will have a complex number here to the n. And if you think about it, you have x plus iy to the n. If you now want to multiply this out, say the n is 100. Think about it. You have like two terms, and you would always have to multiply them out. It's really, really like much work to, if you want to write it again as a nice complex number, something plus I times something. But there are tricks, and the trick is of something you probably very well know, namely polar coordinates. So okay, so in order to simplify this expression, try to use polar coordinates. And let me just recall the main point here quickly. So if you have a complex number z, x plus iy, then, well, it's an absolute value times I phi, or let's say theta. Try to be close to the book here. And, well, theta is the angle of from the x-axis away, and so this is theta is between, let me write this here, 0 and 2 pi. Okay, that's one way how you can do this. If you do that, now you can also use the cosine sine expression plus I sine theta. Okay, so this is how you can write a complex number, if you like, as polar coordinates. And why does this help? So because now you see, if you take z to the n, you take a nth power, and you want to do it here, You don't know how to write it again in this form. While it's, of course, here much easier. It's z to the power of n, e to the I n theta. So you get like, we can just take it in here. And now, see what we have here. Well, we're still in this. And now, for this equation, we can plug this into here. And the expression, we're done. Because now we have a real number plus I times a real number. Well, we can multiply this in here. And so this is a nice, easy expression, looks much nicer. And so once you write the characteristic roots in polar coordinates, everything here becomes much nicer. So please have a look at the examples. So we come to the last case. This is case C. This is a case where R1 is equal to R2. So this is a real, if you like, a double root. Call it R. And how do you how do you proceed in this case? Now, this is something where it's very hard to come up with this on your own. Namely, again, of course, we know that R to the n solves the recurrence relation. So, multiply a constant will still satisfy recurrence relation. You've seen that. But how can you come up with something more? So the idea is if you know about linear differential equations and maybe about linear algebra a little more. So here actually we really would like to have, so we would like to have like a two-dimensional solution space. So what I mean is like we have two initial conditions, and so we need like we have to wiggle around with two variables, but here we only have like one. We only have one constant, not two. And so how do you come up with a second one? That is our A1. Well, what you can check is if you look at n times r to the n, in this case, so you might want to do this, you will find out that this also satisfies the recurrence relation. And so A2 times n times r to the n does, and so this also solves the recurrence relation. And now we know what to do. This is what we want to have. And so we only have to check that the initial conditions hold, and that we just do that again by plugging in n equals 0 and n equals 1. So okay, again plug in n equals 0, plug in n equals 1, solve for A1, A2, and then you're done. Because on the right side we will have a solution having the right initial values and on the left side, so they have to be equal. And so please look at the examples in the book. Let me just write down the most important ones. And of course, do the exercises. So this is for A 10.9, 10.11, 10.12, 10.15, 10.16, and 10.19. So a complex case, 10.21 and 10.22. And finally, there's not so much about the multiple case, root case, but please do also look at it, because as you see here, it's not harder in any way. Just like you have to know about this. You need additional n here. Okay, so that's it. See you next week.